Okay then. Good afternoon. Thank you very much, everybody, for being here today at this Congress. We're going to start with our panel for water and agriculture. As you all know, this agricultural irrigation represents the biggest consumption of fresh water in the world, and the agriculture is the main suppliers of food for the population, with roughly 60% of it. Given the growth of the population with the amount of water that, of course, is limited and the availability is lower because of the climate change, water is not enough, as the superintendent says. And that is why we need to find the new sources of water, as there is the reuse of water, desalination of wastewater and of salty water. And also in this panel we've got a group of many people from the agricultural world, and also for the water treatment, and also for the development of projects, and they've got lots of things to say to this, to contribute to this discussion. And it's not only if we can use new sources of water for agriculture, but how they have been doing this, how it is done, and how do we see it in the future. So as I said, the discussion is not about availability, but it has to do with the combination of elements that will make this feasible with these sources of water, and that will be economical, profitable, and that can be a factor of development for our country or region. So we can welcome our participants, and each one of them is going to have a 10-minute presentation. So once we finish with the round of the 5 presenters, then we can go to the Q&A session. First of all, I would like to invite Maria Emilia Undurraga from San Sebastian University. She is an agronomist, and also she's from the Catholic University, a Master of International Development of Duke University, and she has been supporting the entrepreneurship of female farmers. She has been working as a national director of the National Studies and Agricultural Studies of ODEPA, and she had the first strategy for sustainability in the sector. Today she is working as a dean of the Natural Sciences of University San Sebastian, and she has been working in the territory by promoting the balance of the socio-economical aspect and the conservation of the nature. Maria Emilia, thank you very much. Thank you, Ivo, very much. Good afternoon, everybody. Thank you very much for the invitation to talk about something that is so important. Give me a second, please. But in the meantime, I'm going to thank the conversation that we just had. Now it's working? Perfect. Okay, then. Thank you very much. We already talked about the general framework, and we were able to have some details of the regulation that sometimes it is a bottleneck. But this panel will start talking about why we're talking about it. Ivo said that about 75% of water is used for agriculture. But the first invitation that I would like to do today is to take it to a new point of view, because we are not talking about water for agriculture. We are talking about water for the food that we need, each one of us at home. When we take this conversation and this tension that is quite urgent to have a separation, if it is water for human consumption as it is in agriculture, and if it is just a problem for some that is also outside the city, then this will go to a broader area where we include the agriculture as part of this feeding that needs to make sure about the food safety. When we talk about water and agriculture, we're not going to only be talking about this. We're talking about feeding and also about development of those 263 rural areas in Chile that live out of the agriculture, and that is in the framework of the SDGs. The second one is zero hunger. And that is going to be achieved not only because of the agriculture, but when we've got water, but with more technology. That's why we've got the all of this purpose of these objectives is going to be even more important because we will have an increase of the demands of a 20%. Understanding that the increase of the world population, and this graph will show us. This shows the prevalence of hunger and the amount of people in the world that live in hunger. And 800 million people, they have hunger in the world every day. And for the farmers, that is our purpose, that sometimes we are in the farm within this, we were thinking about how to produce it, but we forget that the purpose of all of this is to feed people. And when you take a look at this and you see that curve, after the pandemic, and specifically after the Ukraine crisis, that went deeper. And from the year 2015, when we've got these SDGs, we haven't been able to reduce the number, but it has increased.
And this is the case of Chile. When we talk about this here for our country, when we talk about water for our food, we're talking about water for a consumption. Chileans spend, according to the last survey of family budget, 21% of their budget in food. And in the most vulnerable homes, it's about 32%. So a third of the budget of some Chilean families is spent on food. And that means that using water to produce food is thinking about not only the farmers, but also how we can have food security for all of our citizens. This is what we're living lately due to the Ukraine crisis. We were facing a very high inflation in food. We still have about a 28% and 8% inflation rate on food, and that's hitting the most vulnerable families very hardly. But when we talk about agriculture, let me give you a small context, because I know that not all of you come from an agricultural background. So about 17% of our land is used for agriculture. It's only 17% of all the land in Chile used for agriculture, mainly meadows, and only 10% of all that's used is used for the yearly crops and fruits. And we also have the forest in that graph. As an economic activity, what does it represent? It's an employer for 618,000 people, and this is only as direct employment, and it also represents about 20% of our exports. So 19 million in revenue that allow us to buy those goods and services that we can provide ourselves in our country. And since the nexus is not always agriculture, it's how does it translate to what we eat. In Chile, we produce about 70% of the wheat that we eat, 40% of meat, 76% of milk, and as you can see for fruits, it's about 99%. And so we as a country, we have specialized in the production of certain foods that we can export and eat, and we also have those products that require a lot of water. For example, why are we exporting when we have a drought? Well, if we put all of that in a balance, it's about 9 billion that we export in food. But if we make the same balance for water and see how much we use to produce that, what we export, and we subtract the water that's used abroad and that we import, the balance is positive. We are importing water. What do we import? Meat and cereal, the products that need the most water to be produced. And now, I also wanted to mention, and I am biased, I have a rural bias and a regional bias as well. We'll talk a lot about averages, but in the field, we don't use averages, because what's happening in all of the basins and all of the different parts of the city do not reflect the average. So 73% of water is used in agriculture/food. But if we translate that into the regions, we can see how yellow, which is agriculture, and blue, which is mining, and which on a state level is only 3%, you can see that in Antofagasta it's about 50%. But when we go to Los Lagos, where water is not that relevant for agriculture, industries become more important. So when we analyze where is water spent, who spends water, it's very different region to region. And now I'm going to move to water in agriculture. About 7.8 million acres are cultivated, and only half of them are watered. The other half don't require watering. They water themselves through rain and so on. So we need infrastructure that use the watering, and this is something that's very different between different crops, obviously. Fruits, for example, are completely technified with dripping systems, and then other crops that require less watering. And when we're talking about watering, innovation is very important, and we have to incorporate it in agriculture. We need to move forward in technifying, because most of it is still through something that's very inefficient. And in agriculture, there's a lot that we can contribute in the sense of water security. We have had several instances of civil society, public and private entities to discuss about water. And it's very important, as Maria Jose mentioned previously, to see this integrally in management. This is the integrality of management. This is not only security, this is quality as well. This is something that was mentioned in some of the questions. This is the legal framework. There are pillars that are transversal to allow for this adaptation to this new condition of climate change. Why? Because this has to be done in a way that's different, not only according to region, but for every basin. We have 101 basins, and there's a lot of diversity among them. And the solutions, as were mentioned in the previous panel, we have different solutions depending on each basin. The same solution cannot be applied to every single basin, and understanding this is going to allow us to implement solutions that are going to reflect that reality. And now, what are some of the challenges and the opportunities? The great word here is adaptation. We are a small country. We can't do very much in terms of mitigation. Of course, we must get on board in carbon neutrality and so on, but we emit such a small percentage of the greenhouse effects, and yet we are one of the most affected countries by climate change. So our focus has to be on adaptation. We have to adapt ourselves, because we're going to be hit by climate change, and water is going to be a huge element of it. This graph reflects hydric balances. This means how much it rains minus what is evaporated, and this is the current situation. And when we project this to 2050, this is the graph for the central zone of our country. And that means that the projection is that we're going to have a very big hydric deficit that is going to be very different for each region and for each different sector. And it's going to require a coordinated action. And now I'm going to move to the last slide. These are the challenges and opportunities that must not only focus on getting new sources, which is the focus of this seminar, of course, but we also have to combine this discussion on the new sources with the objective, which goes beyond, which is being more efficient in how we use water in agriculture, not only having more water, but becoming part of the challenge of producing more with less water for a population that requires healthy eating, how we can make progress in infrastructure, and how we can avoid neglecting water quality. And public policies for water are going to be fundamental for this adaptation process. Now, I want to also mention that in the Universidad San Sebastián we have a focus that's very broad And I have several integrants of our Special Center for Water. We have a view that has different conceptions of the uses of water: social, environmental, and economic. Separate, for example, the importance of mining and agriculture and health. When we have integral answers, we're going to be able to show a solution that leaves nobody behind. And this is something that we're going to talk about with the other panel members, because this is happening in other parts of the world. Thank you very much. Thank you very much, Maria Emilia. That was a great analysis in a very short time. Now we have Professor Luis Gurovic, who is from HEA Consulting, a forest engineer from Universidad Agrónoma and from the Israel Institute, and over 30 years of experience in surface watering systems and the development of watering systems, as well as the efficiency of watering for different crops, working for different companies, agricultural companies, and experts, civil engineers, hydraulic engineers, as well as an academic from Universidad Católica. His activities include different research, scientific research that has yielded over 4 textbooks on agricultural water systems and published in several journals. Luis Gurovic is the president of the Association of Watering Systems and his current president. Please be welcome, Mr. Gurovic. Good afternoon, everybody. Thank you very much for your presentation. I'll use my 10 minutes to talk about something very concrete. And the question is, if desalinated water is a solution for the future of agriculture and the watering of agriculture. Let's not forget that agriculture produces over 75% of the food that's eaten worldwide and consumes 75% of the fresh water that is available. So the answer to this question is desalinated water the solution for the future of watered agriculture? And the answer is both yes and no. And now we'll see why. How much water does watering agriculture need? In terms of volume, and I'm talking about a national average, we're talking about 6,500 cubic meters per acre. That's about 6.5 million liters per acre that are consumed in agriculture. That's much how plants use. Well, it's actually the weather, but it goes through the plants. So we blame the plants. But that's not all. We also need a flow, because the amount of water that's needed is not the same throughout the year. And during different times of the day, we're talking about 10 millimeters a day, which means 100 cubic meters per acre every day. That's how much we use during the hottest months of the year. And in agriculture, we also have periods when we water and times when we don't rain. We water from the spring throughout the summer and part of the autumn. So during 6 months, and the other 6 months we don't use water. And there are critical epochs, which are 40 days during the summer. About December 15 to February 15, we're going to have those days where we're going to use the most water. So we have to consider that we have to stock water when we're not using it. And we also have to distribute it. And both activities have a cost. And we're going to see that it's not a minor cost. It's very important when we consider hydric resources. So how much seawater or salty water is being desalinated today in the world? We are currently desalinating the water needed by 500 million inhabitants worldwide, and the World Health Organization has said that we're going to need 160 liters per day to fulfill the requirements of a society that has enough water security. In some parts of Chile, we have 25 liters of water a day because we don't have more availability. That means 62 cubic meters per inhabitant per year, and we're going to add on top of that another 15%, which is the water that is needed by mining and industry. So desalinated seawater, we are using 36 million cubic meters every year, and that's what we call non-consumption use of water. So if I take all the water that is desalinated and I apply it to agriculture, we are watering 5.5 million acres, so about 2% of the total. So the future is looking very promising. If I'm watering only 2%, I still need 98% left to go. Well, today we're only using 0.5% of desalinated water for agricultural watering, only 0.5%, and that is equivalent to 275,000 acres. Which acres? Those that have very valuable, commercially valuable crops and that are produced in high technology greenhouses. So tomatoes, for example, for the most important cities in Saudi Arabia, because they can pay for desalinated water. That's why we have so little surface that is directly watered by desalinating plants. So it's very, very little. And the reason for this is that agricultural crops are not profitable enough to justify the cost of desalinated water used directly in agriculture. What is the cost of desalinated seawater? In an reverse osmosis plant of cutting-edge technology, a large facility that produces drinking water for about 3.6 million people. We're talking about some 624,000 cubic meters per day in terms of production. We reach $0.58 for each cubic meter, which is the OPEX, and 0.17 is the CAPEX. So the necessary capital required. So this is the plant of Sorek B in Israel, which is one of the most advanced plants and efficient plants in the world. So that's the cost for such a plant. And smaller plants are going to have a value that's going to be slightly higher because we have scale economies. So if we look at agricultural consumption of 6,500 cubic meters per acre, only in the production of water we're going to pay about $4,000 for acre, and there's no crop that can pay that additional cost, only in terms of production. I'm not even talking about the capex for the distribution of the water, which is valued in $0.1 for each 100 kilometers in distance. And I'm also not including the OPEX for distribution, which is $0.2 for cubic meter for every 100 meters in height that we have to pump the water for the production valleys. So water is very, very expensive. Is this bad? No. Fortunately, we're not that bad. How was this dilemma solved of the unpayable cost of water for agriculture? First of all, by moving all the production of desalinated water for another use, which is drinking water for the population. So the prime use of desalinated water is going to the population as drinkable water. Then we collect all this drinking water, which we call the effluent, and we give it and we treat it. We give it as primary, secondary, and tertiary sanitary treatment so that it can become water for watering, and then we have a second use, and that's when desalinated water can be used for agriculture in a commercial point of view, and that's what is being done today in the world. This water, after being treated, must be distributed. We must bring it to agriculture, and that's why the countries that are working seriously on this issue have created a network of pipelines of purple pink color, as you can see, which moves treated water to the farmer, which is different from the legislation that we have today that forces us to discharge the water into the natural basins, which is a very big limitation. What is the secret for this to work in countries such as Israel and others? People have been sincere about the cost of water in terms of its effective cost in production. Every consumer pays for it. The first process is paid by the people that use that drinking water, and then the second use is paid by the farmers, and what they have to pay is the sanitary treatment that is applied to that water and the distribution, of course. When those situations have been accomplished where people actually pay for the value, then the business works perfectly, and the concessions that have been made to desalinate water and its use, first of all by the people, by the city, and then by agriculture, lasts only a few years, 5 years or even less in some countries, because the companies, if the company has the concession and has done it correctly and has fulfilled its pledge, then it's going to be renewed automatically. And if it hasn't done a good job, it's going to lose all the invested capital because it hasn't followed the law. And that's why the whole control system is a very small system with very few people working there, and which can be done very quickly, because you have to ask yourself, did they fulfill their part of the bargain? And if they did, then it's renewed.
So summarizing seawater, first of all, we're going to treat them so it will be drinkable water, then will be residual water, and that will be taken to irrigation. Why? Because we've got the costs associated and the volumes in which we're going to use those volumes in the agriculture. And also we have developed something additional to have a new agricultural areas such as the Salachapa, Trancha, and Green Atacama, that in Chile those are areas when we've got pretty much no agriculture, and also they are produced in that area because of the climate, and that are a crop that is of a high area. So this is very small, and using this seawater in some areas, in populated areas, those are provided with desalinated water if with that is favorable. What does it mean? That we can also do some swaps, some geographic swaps, leaving the valleys that are up in the water, all the water available for the current irrigation, and the desalinated one for the coastal areas. So with that, we avoid the cost of transportation from one area to the other. So that will remain in the fields, but in the populated area, this is going to be desalinated water for the use in the city. So imagine that what we have heard here is the legal complexity to do all the swaps and the investments in the infrastructure that are needed, that will make these topics of the swaps, that is going to be something that I consider that is something quite complicated unless it is the situation in other countries. And also for the direct use and the agricultural production is the objective price of the water that would allow to assess if the project can be profitable and sustainable considering the real cost of the desalinated water. So the paradigm is that we need to move the discussion from the agriculture doesn't flow with the desalinated water price, and given the price, what sort of technology and cultivation can allow us to do this. This is not going to solve the agricultural problem, but in some projects probably this will be of a high profitability. To finish, what is the context up to the year 2023, what is the percentage of seawater is used for urban consumption and industrial consumption because of the reverse osmosis? Singapore, 90% of all the water of Singapore is desalinated water from the sea. They don't have any other source. The other 10% comes from algae vessels because they don't have water in the island. Israel is the region of 78%. And what is the percentage of the urban effluents on industrial that is treated in order to be used as irrigation in the agricultural crops? Where in Israel we've got a 92%, in Spain it's 27%, and in the US it's the 11% of the total water that is wastewater is treated to be used in agriculture. So there is a long way to go. And let's put this into context. If we take the water out of the 19 million Chileans, all the water that is generated of the 19 million inhabitants, and that is calculated with 170 liters per day, we will have to do a treatment of over 1,000 million cubic meters per year. Someone mentioned something similar. If we made that a huge effort to give treatment to all the wastewater, to all the inhabitants, then maybe we will have to irrigate 16.5% of the surface. Of course, we're not going to reach that number, so the contribution that we may have from wastewater will reach less than 20% of the agricultural areas. There are 350,000 hours that represent this drip irrigation that correspond to the 50% of the total irrigated area, and with that we're world leaders, and currently in average we've got some 20,000 hectares that are being implemented with high technology, and also all the areas that are being left aside because of the drought. We are moving forward in terms of technology. What will happen with the industrial areas? That there is a problem of legal ownership, but we don't know who those water belongs to, and then we don't have, we've got just the primary and the secondary processes for the wastewater, and we've got a 22% that is left aside that correspond to dropping or discharging that untreated water to the sea. And also the water desalination by means of reverse osmosis has a cause of production and conduction and distribution. And the huge problem in our country that we have seen here is the problem with the permits, where any idea, it doesn't matter how wonderful and brilliant it is, this is going to be diluted because of this bureaucracy that we've got in our system. So what's coming for the next 15 years? We will have the agriculture for the south and central south area. We will have crops with a higher value because we've got a very good market for the exports, and most of the new areas are going to be irrigated through pressurized system, and the monitoring through the phatic system that will have an understanding of the hydrology of the basins, which is a challenge because we don't have it. In the areas of new agricultures, we're going to use wastewater in around 2 million inhabitants, in small plants between 50,000 and 200,000 inhabitants, and that our water will allow us to irrigate another 150,000 hectares. And it seems that no seawater that is desalinated is going to be used for the farms because first of all, there needs to be used by the population. And we've got this treated water. We consider it the better use of this seawater, first of all, for the urban use, and then for a second agricultural use. So thank you very much for your time. Thank you, Luis, very much for your vision. I would like to invite Beatriz Saiz from the GS INIMA. Beatriz, please. to give you an example of the use of this water in the agriculture. First of all, I'm going to give you a brief introduction, and then I'm going to explain you this plant, and then I'm going to finish with some key ideas. Since I'm the first one in presenting, then I just wanted to do an introduction of the GS INIMA environment. This is one of the companies where a higher number of projects of water treatment belongs to the GS group, which is one of the most important groups in South Korea. We are experts in water, energy, depuration, desalination, industrial water, and we also include renewable energies as part of our plant solutions. We're also able to act in every phases of a project, starting from the engineering, construction, concession, maintenance, and we have been working for 50 years being pioneers in the environmental sectors. We've got some projects such as the first desalination of the world in Great Cape, and also the carbon-free, which was the first desalination in Europe in 2018 for human consumption water in Atacama here in Chile. And last but not least, in 2020, the biggest desalination plant in Oma. We're a company which is global, with our global presence, which is in 4 of the 5 continents. And just to explain the topic that gathered us together, I would like to give you an idea with the desalinated water and the use in Spain. Currently, the agricultural sector, they use more than 70% of fresh water in the country. In Spain, we've got 3 million cubic meters of desalinated water, and more than the 21% of this water that is produced is for agriculture. But if we've got the whole balance of water that we use in the area of agriculture in Spain, only 1.8% is represented by desalinated water. And the Mediterranean basin constitutes one of the areas of desalination that is very important, and we need to have this sort of desalination that will have this water for the use in agriculture. So we will have this dam of Tierra Vieja in Alicante, and also in Campo Dalias in Murcia, and the island of Carboneras in Almeria. For the last 20 years, this is the company that is in charge of the operation and maintenance, and this is the plant that we wanted to choose to set an example of a desalinated company that is going to be set for agricultural use. How is this project coming? From the island of Carbonera, because of the water scarcity that this zone had. So the aquifer were pretty much depleted, putting the survivors of many of the agricultural businesses at risk. So that's why when the government and also the group of farmers, they will promote desalinated that will be able to supply this for human consumption, and also for the coal industry, and also for the irrigation in these areas of Níjar. So the promoter is Aquasur, which is the current Aquamed from the Mediterranean basin, and the contracting company was the UTE, that is from Endesa and GS INIMA. They started with the construction works in the year 2000, and at the beginning of the operation takes place in 2004. This plan has its production for the human consumption and also the use in agriculture, but also for industrial water, because they've got a thermal industry, and part of that production, or a small part, has to do with part of the process of this thermal plant. With this, we are able to supply the 120,000 inhabitants in and another 1,000 and 7,500 hectares are close to this Níjar. This was, for many years, it was the biggest plant that was created in Europe until the one in Barcelona. Taking a look into this technical data, we've got a production capacity of of 43 cubic meters per day, and also we've got desalination. We've got two main lines of 60,000 cubic meters per day, and a conversion from seawater to the finished product of about 45%. Here we can see the water quality that was captured and the water quality that is the product, and we will comply with the royal decree, which is that was derogated by the number 3 of 2023 for human consumption. This is the line of treatment for the plant. I'm going to explain that, but I wanted to say that this is a conventional treatment. It's not for agricultural use, and some of the 3 uses that I just mentioned, we need to have a specific treatment. The treatment of the plant started with the capturing of the seawater, which is confirmed by 2 open towers, and also we've got a distance of 1,500 meters from the coast, and then reach the plants that will have a chemical pre-treatment to oxidize the organic matters and to do a pre-disinfection. We also do an initial physical pre-treatment going through 6 channels of desalination that would eliminate the sands and also the limes, and the 6 pumps that can do this aspiration are in the area of aspiration. So to continue with the pre-treatment, we've got the pre-treatment in the filters. The water will go through 22 horizontal areas under pressure and with a different granulometry. The filters are clean with air and brine, and the last part is treatment and going through the water with the 2 units with this cartridge of 20 microns. And once we've got the pre-treated water, that this is sent to the membranes of reverse osmosis because of the high pressure pumps which are organized in the collectors. And they're able to send the water at a pressure of 70 bars. This stage of reverse osmosis of this plant is configured in 2 parts. On one side, we've got the water that is for human consumption and for its use in agriculture. That is a part of the first stage, which is constituted by 12 areas and also 12,000 members that are in the first stage. And part of this permeability that will go to a second stage of reverse osmosis that would allow us to have a permeability with a TTS that is below the 8 ppm. So this is the second stage that is going to go to its industrial use in the injection of the turbine. The rejection of this reverse osmosis and the brine that will go through Pelton turbines that would allow us to recover the energy because of the pressure in the ones that we will have the brine in the reverse osmosis. And once we've got this, so this is going to be stored in treated water, and then this is going to be distributed to the different areas or whatever we will need for this. In the case of the water for human consumption, we need a remineralization of water by the CO2, and also we're going to have a small adjustment with the sodium hypochlorite. This plant has a particularity that there is a thermal plant that is next to it. So the flow of the cooling system has a flow which is 20 times higher than the current over a brine, because up to now we have been sending this brine to this channel from the channel of this cooling system. So we've got a synergy between the 2 plants. So as I said, this is an old plant that was built in the year 2000. So with that, we've got some improvement works. We've got the substitutions from the Pelton turbines by pressure exchange of rotation dampers, and then we're going to change the engine, and we are going to have a different system, and we're going to incorporate new lines for reverse osmosis with a higher production that will substitute the old ones. And given this and this has reached the last part of the life cycle. We are going to have an emissary for the discharge of the brine, and with that we can comply with the environmental regulation in force. This is just for you to have an idea for the distribution data of the water because of its use. That 68% of the water because of this plant will be designated for the fields in Níger, and the next the rest is for Mojácar and Garrucha, and only 2% is going to be testing for the use in the thermal plant for industrial use. Some final ideas that I would like to share about the use of desalination and what can bring us for the use of water in agriculture. On one side, it is quite important that desalination can guarantee the water supply. There is no water that we don't have, and with that, it can generate some social problems of development and so on and so forth. On the other hand, the water that we've got from desalination is a la carte water, and actually, if we're going to need an additional treatment for that water to be used in some specific cultures, then we will be able to optimize this treatment afterwards, because the water that we're going to receive is going to be pretty much the same all the time. And then let's keep in mind that the availability of this water can also imply or have an impact in the survival of the local businesses and also to launch their production. The more water we've got, then the more things we can generate. And finally, let's not forget that desalination is only one of the resources that we've got at hand to face the overexploitation of the aquifers and the combination of the different methods that are available. That is the one that is going to allow us to do so. So thank you very much for your attention.
Thank you, Beatriz, for bringing such a concrete and real example, and also all over 20 years old. Please be welcome. Good afternoon. First of all, I would like to thank you for the invitation to present and to tell you about the project that we're working on. As an introduction, the previous presentations have talked about the water shortage that we're going through, and I can't add no information to what has been talked about. But the central and northern part of Chile is going through a desertification process due to climate change. And given these consequences, we can see an increase in temperature, a reduction in rainfall, and a reduction in water resources. Furthermore, in a context of climate change, by 2030 we're going to expect a reduction of 60% of hydric resources for the northern region, and we're also seeing an increase in water shortage for agricultural emergencies, among others. There are several decrees about water shortage that affect over 200 municipalities of Chile. In a regional context, let's take a look at the region of Valparaíso. 80% of the desalinated water, of water consumption goes to agriculture, and 12% goes to human consumption. In national terms, this is similar to what was mentioned before in previous presentations, which can be seen that in a national context was about 60% was aimed at agriculture. Given this context of climate change, it's urgent to search for new water sources, as has been mentioned before and in presentations by the previous speakers as well. And in this sense, reusing water and desalinating water is very important both for human consumption as well as for agriculture in the long term. Among these alternatives, the use of desalination, as Beatriz mentioned, is more expensive but has some advantages. For example, desalination is an unending resource that doesn't depend on climatic conditions. So this is something that we can plan for the long term, both for agriculture and human consumption, and even productive processes. It creates a high quality product that can be used for several different uses. And other aspects that's important, we can adapt the water for the final consumer, be it a farmer, be it for human consumption, be for the industry or whatever. So we can plan in the long term, for example, for agriculture, to improve, to transform agriculture to more modern agriculture, and thus increase production or improve efficiency, which can be seen also in Spain. Now, in the national context of Chile, currently there are 28 projects either ready or under construction that are aimed towards industry, as we talked about today, mainly mining. But how many projects are aimed for human consumption? And let's say that a minimal percentage is aimed at agriculture. Factors. One of the most important is the cost of salt water, which is one of the main concerns for agriculture. And another one is the lack of knowledge at a national level and empirical data to study the viability of desalinated water for agriculture in Chile. For this reason, in this context, the project that we're working on is born. And in our project, we have financing from the research agency with over 2 million pesos, and it's going to be carried out over 4 years, and it emerged as a knowledge transferal project and entrepreneurial project as well. What's the objective? We can summarize it in 2 objectives. First of all, identify the best thresholds of quality for desalinated water and the viability for existing crops and emerging crops. And at the same time, as its second goal, to study the economic viability of these crops when they are watered with desalinated water or the mixture with other crops to find the most optimal production conditions. We have generated different alliances with both public and private entities, such as the regional government of Valparaíso with the very governor, the municipality, different institutes of sciences, and so on. And we also incorporated the farmer communities of Puyalli. The project is located in an agricultural land in Papudo, and it collaborates with one of the farmers, who is Jesus Bazas, who is known as the King of Quinoa. It is also important to highlight that under this wing of collaborating project, we also work with Vigaflow, who also contribute from their pilot desalinator plant and with the technical knowledge and engineering knowledge necessary for making the plant work. In the first instance, the project starts as an idea to capture seawater, since our land is located next to the shore, but there's also an underground basin that has become more salinated over time and has made it impossible for certain crops to grow. And so we had the opportunity to rethink the project to use salty water for capturing, and thus reducing the cost of capturing seawater, and thus reducing the cost of the project. And so we used this opportunity for our project. How did we start for this project? We had all that was needed in terms of knowledge, technical knowledge, and so on. And so we started with the very first crop, with an experimental crop, as you can see on the picture, using 3 different treatments. Salty water, a mixture of 50% salty water, underground salty water, and a third treatment with well water from a well. So we only had to choose which crop we were going to grow, and we decided on strawberries for 2 main reasons. First of all, It's a crop that's being developed for over 10 years in the sector, but we stopped growing it because of the loss in productivity in the area, and secondly, because it's a very sensitive crop. So this allowed us to compare the different treatments with much more detail. So, what are the results? In productive terms and in growth terms, using different parameters such as the growth of leaves and the plant and so on, we saw that there was a considerable difference when used salty water and the mixture of waters. And another very important result that really surprised us after 7 months of experiment is that the mortality of the crops was highly reduced when used desalinated water when compared to salty water. That was the hypothesis that we were working on from the knowledge of the farmers from the zone. Well, a picture is worth 1,000 words. So here are a few pictures that compare the crops with desalinated water and salty water, and you can clearly see the difference in quality and size of the crop when we use salty water and desalinated water. However, we also wanted to make some progress and also do some lab analysis with different indicators such as associative stress, both for the leaves and the fruit. And I don't want to get into the technicalities, but the most important thing is that we use an indicator to see the stress